This is the last section on chapter 5, which is on matrix algebra, and this section is on the Cayley Hamilton theorem. Now, the Cayley Hamilton theorem states this, and that's this: every square matrix, so 2 by 2, 3 by 3, 4 by 4, and so on, satisfies its own characteristic equation. Now, what does that mean? Here's an example. So if I had a matrix M, a square matrix M, and it had a characteristic equation which was lambda squared plus a lambda plus b equals 0, then m squared plus am plus b times the identity equals 0, and this should be the 0 matrix. I'm going to underline that. So you can see that the coefficients here are the same as the coefficients of the characteristic equation. So here's an example. So I know that this matrix, I'll call this matrix M, 4, -5, 1, -2, has this characteristic equation: lambda squared minus 2 lambda minus 3 equals 0. And you can check it for yourself, but this is one that we've worked out in a previous example, and this is this characteristic equation. Now, what does that mean? Well, by the Cayley Hamilton theorem, and if we're going to use this relationship, then we should say that this is by the Cayley Hamilton theorem. M squared, so this matrix squared, minus 2 times this matrix minus 3 times the identity equals 0. Now, stating that fully, it would be this: 4 minus 5, 1 minus 2, times by itself, or squared. So I could put this: 4 minus 5, 1 minus 2. So this is m squared, just tie that one up, minus 2 times m, that's 4 minus 5, 1 minus 2, minus 3 times the identity, 1, 0, 0, 1. That will equal 0, 0, 0, 0, the 0 matrix. And what you can do, you can multiply this out and check for yourself that actually this relationship does hold. Okay, let's get into some examples. So demonstrate that this matrix satisfies its own characteristic equation. So we're actually going to have to first of all work out what the characteristic equation is. Okay, so this is going to be the determinant of this, so we should be used to doing this, equals 0. So we will have 5 minus lambda times by 3 minus lambda minus 3 times 2, which is 6, equals 0. So we get this characteristic equation. So 15 minus 3 lambda minus 5 lambda, so minus 8 lambda, plus lambda squared minus 6 equals 0. So that's going to be lambda squared minus 8 lambda plus 9 equals 0. So if matrix A here is going to satisfy its own characteristic equation, then we need to show that A squared minus 8 times A, matrix A, plus 9 times the identity equals the 0 matrix. So we need to show whether this is true. So now it's just about doing calculations. So 5, 2, 3, 3 squared, so we're timesing it by itself, 5, 2, 3, 3. Then we're going to subtract 8 times A, so that's 5, 2, 3, 3, so 8's the scalar, plus 9 times the identity, and we want to see if that gives us 0. Right, so first of all, let's multiply out these two matrices here, basically A squared. Right, so we're going to have 5 times 5, which is 25. So we've got 25 plus 6, which is 31. moving off to the second column, we're going to have 10 plus 6, which is 16. Bottom row, we're going to have 15 plus 9, which is 24. And the last one, we're going to have 6 plus 9, which is 15. Now we're minusing 8 times this, so let's actually write minus, and we'll multiply all of the elements by 8. So we've got 40, 16, 24, 24, and then we're adding 9 times the identity, so that's just going to be 9, 0, 0, 9. So let's see what that gives us. Right, so what I'll do is actually write the calculation for each element. So for the first element, it's going to be 31 minus 40 plus 9. Okay, so you can see it's just the first elements there, 31 minus 40 plus 9. For the second element, that's going to be 16 minus 40, sorry, 16 minus, looking at the wrong elements there, 16 minus 16 plus 0. The third element is going to be 24 minus 24 plus 0. And then the last element is going to be 15 minus 24 plus 9. Now you may have worked it out already that 31 minus 40 is negative 9, plus 9 is going to be 0. 16 minus 16 is 0. 24 minus 24 is 0. 15 minus 24 is minus 9, plus 9 is 0. Okay, so we've shown that this matrix satisfies its own characteristic equation. So we can just write a conclusion. So A satisfies its own characteristic equation. Okay, so here it says, given that A is this matrix here, first of all, find the characteristic equation of A. That should be easy enough. So we want to work out what that characteristic equation is. So that will be the determinant of 1 minus lambda 2, 3, negative 3 minus lambda equals 0. So that will be 1 minus lambda times by negative 3 minus lambda minus 3 times 2, which is 6, equals 0. Multiplying out the brackets, we will have negative 3 and then minus lambda, I'm going to write it out because I don't want to make a mistake, minus lambda and then plus 3 lambda and then plus lambda squared minus 6 equals 0. So that will simplify to lambda squared and then plus 2 lambda minus 9 equals 0. So there's our characteristic equation. Now in part B it says hence show that A cubed equals 13A minus 18 times the identity. Okay, so we must start with this here and write down the relationship we have using the Cayley Hamilton theorem. So by the Cayley Hamilton theorem, and whenever you use any type of theorem, you should always make a statement that that's what you're using to get your assumption. So by the Cayley Hamilton theorem, we will have A squared plus 2 times A minus 9 times the identity equals 0. So if we compare what we've got here with what we're trying to prove, we've got an A cubed. So I think the first thing we're going to do is we're going to multiply both sides by A. So when we do that, every term is going to get multiplied by A. So then we will have A cubed plus 2 times A squared minus 9 times A, because the identity times A is just going to be A, equals 0. So obviously if you multiply the 0 matrix by A, it's still 0. Now you'll notice that what we're trying to get to has no A squared term in it. We've got A squared term here. But we can rearrange this to make A squared a subject, substitute it here so that we can eliminate A squared. So we need to eliminate, let's make sure we spell it properly, eliminate A squared. And the way we're going to do that is by substituting in A squared. So we'll rearrange this to make A squared a subject. So A squared equal to, so we'll add or take away 2A from both sides, and then we will add 9I to both sides. So that will be what we substitute in. So what we'll have now is A cubed plus 2 times this here, the substitution. So 2 times by negative 2A plus 9I minus 9A equals 0. So we'll multiply out the terms. So then we'll have 2 times by negative 2A, which will be negative 4A, and then plus 18I minus 9A equals 0. We want to get the A cubed term on its own. So what have we got? We'll add 4A and 9A to both sides, so that will give me 13A on the other side. And we'll take away 18I from both sides. I will end up with this as required, or we can write QED to show that we've demonstrated that statement is true. Okay, so part A of this question asks us to find the characteristic equation of M, that's this matrix here. So the characteristic equation is going to be the determinant of this matrix, or it's the 2 lines tell us it's the determinant. So we just put minus lambda along the leading diagonal. So here we go. And that's going to equal 0. So the determinant is going to be 1 minus lambda times by its minor, which is negative lambda, so I won't write the 0, 2, 1, negative lambda. Then minus 2 times its minor, so that's going to be negative 1, 2, 2, negative lambda. And then plus 1 times its minor, and that's going to be negative 1, negative lambda, 2, 1, and all that equals 0. So let's now multiply that out and work out these determinants. So we've got 1 minus lambda, and that's going to be multiplied by, so these are going to be easy to work out, I think. So that's going to be lambda squared minus 2, lambda squared minus 2, then minus 2 times by, and this is going to be lambda minus 4, lambda minus 4, and then plus 1 times by, and this is going to be negative 1 minus negative 2 lambda, so that's negative 1 plus 2 lambda, so negative 1 plus 2 lambda. So that will equal 0. So let's multiply out the brackets and see what we get. So we're going to have lambda squared minus 2 minus lambda cubed plus 2 lambda minus 2 lambda plus 8 minus 1 plus 2 lambda equals 0. So that can be tidied up to give us this quadratic. So we'll have negative lambda cubed. Okay, so that deals with that term. We've only got a lambda squared, so plus lambda squared. Then with our lambda terms, we've got 2 minus 2, which cancels out. So it's only going to be plus 2 lambda. So plus 2 lambda. And then in terms of our numbers, we have negative 2 plus 8, which is 6, minus 1, which is 5. So plus 5 equals 0. Now, we can leave it as it is. That's fine as the characteristic equation. Or we might decide, right, let's times everything by negative 1. So we end up with a nice positive coefficient for the cubic. So that'd be lambda cubed minus lambda squared minus 2 lambda minus 5 equals 0. So there is our characteristic equation. Now part B is asking us to use the Cayley Hamilton theorem to find the inverse of M. Now you might be thinking, well, hang on, there is no inverse here, okay, but we could say by the, and I'll just put CH theorem, Cayley Hamilton theorem, this matrix is going to satisfy its own characteristic equation. So we'll have m cubed minus m squared minus 2m minus 5 identity equals 0. Now, if we were to multiply everything here by m inverse, that becomes m squared, that becomes m, that will just become the identity, and we have m to the minus 1 here, the inverse. We can rearrange it to make the inverse the subject. So let's do that. Let's times everything by m inverse. So then this equation becomes m squared minus m minus 2 identity minus 5 m inverse equals 0. So now we'll rearrange it to make m inverse the subject. So if we do that, we will have m inverse equals 1/5 of, because we're going to have basically 5m on the other side, and we'll divide it by 5, m squared minus m minus 2i. So basically what we're going to do is calculate this, find 1/5 of it, and it gives us the inverse. So this is an alternative way of finding an inverse of a matrix. Okay, so I've written out what the calculation would be. So it's going to be 1/5 times by m squared, m times itself, minus m minus 2 times the identity. So I've multiplied the identity matrix by 2, and then the numbers along the leading diagonal become 2. Now just finish this off by closing the square brackets. Now I'm going to use my calculator to work this out. So now it's going to be 1/5 of what I get by calculating what's here. Now the way I'm going to do it is I'm going to define matrix A as M. So I'll make this matrix A, I'll make this matrix B, and then when I do the matrix calculation, I will just do matrix A squared minus matrix A minus matrix B. This will be much quicker if we do it on a calculator. Now I've done this on a calculator, and I've done it manually, and it's much quicker doing it on a calculator, and I know it's going to be correct. And also, you know, if you're going to do it manually, the issue is, like, there's lots of places where you could easily mess up a calculation, an addition, a subtraction, a multiplication. It's easily done. So this is what I get from my calculator. I know the inverse is going to be 1/5 of that, so I'll just leave that out as a factor there. And there we go. By using this Cayley Hamilton theorem, we have found the inverse of a 3×3 matrix. Very useful. Right, you should now be able to do exercise 5D on pages 181 to 182, then followed by the mixed exercise. So just a quick recap. So the Cayley Hamilton theory states this, that every square matrix M satisfies its own characteristic equation. So here's an example of a characteristic equation, and just need to put the B in here. So it'll be B times the identity. and it will always equal the zero matrix. And questions of this type often involve some matrix algebra, so it may be that you need to multiply or divide both sides of an equation by a matrix, well, not divide, but multiply by a matrix or its inverse to get a required form. And we can use the Cayley Hamilton theorem to find inverses, particularly of some 3 by 3 matrices.